In this section, we'll be looking at summations and leading up to the area problem. A summation is the sum, adding things up, of terms within a sequence. And I've got the following summation formulas and properties. So there are 6 of them total. First things to know are this symbol here is the Greek letter sigma. This is what we'll use to tell ourselves that we've got a summation. We're going to have a summation from the term I equals 1, so term 1, to the nth term. If n is 2, then there are 2 terms that we are finding the summation of. If n is 5, there are 5 terms. If n is 100, there are 100 terms that we're going to add together. And I've got the following things. If I'm taking the summation of a constant, so this is just a number, then I can just take that number, multiply to n, have Cn as my summation. If I'm taking the summation of I use the following: n times n plus 1 over 2. I squared will have the summation n times n plus 1 times 2n plus 1 all over 6. There may be times that you might use I cubed, I to the third. That'll give you the summation n squared times n plus 1 to the second power over 4. And then the following properties here are saying if I've got multiple terms of my summation, I'm adding this term plus this term. I can break that up into 2 separate summations then, the summation of the first term plus the summation of the second term. I could also do that with subtraction. The summation of this minus this will be the first term's summation minus the second. That'll help breaking things up will help solve things later on, even though it looks much more complicated in the moment. Lastly, if I've got a constant and I'm multiplying it to some term, say 5i, then what I can do is pop that 5 out to the front, then do the summation of the I, or whatever you've got left, which will be usually one of these here. So let's go over some examples. How do we use this? Well, it could be something simple like this. Evaluate the summation of I equals 1 to 200 of I. Now you could start writing 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way to plus 200, and then add all of those things together. But that's a lot of work. And it's a lot of work. It would take a lot of time. Instead, I use the summation formula for I. Here I've got this separately here. And that is n times n plus 1 over 2. So I just take my last number here. My last term is 100, or 200 in this case. And I say 200 times 200 plus 1, so 201. And then I divide that by 2. I get 40,200 divided by 2. The summation is 20,100. I could do this for I squared as well. Let's say I've got I equals 1 to 25. So the first term would be 1, because 1 squared is 1. The second term would be 4, because 2 squared is 4. Third term is 3 squared is 9. Fourth term is 4 squared is 16, all the way up to my 25th term. 25 squared is 625. I could, again, find all of these things separately, add them together, but that would take a lot of time. Instead, I'm going to use my I squared summation, which is n times n plus 1 times 2n plus 1 all over 6. Well, my last term is 25. So 25 times 25 plus 1 times 2 times 25 plus 1 all over 6. That's 25 times 26 times 51 all over 6. And simplifying this gets me down to 5,525. Certainly a lot less work, I'd imagine, than finding all of these squares and then adding them together. But there's also going to be problems that are more complicated. such as this. Find the limit of S of n, some sequence, as n approaches infinity. So S of n is going to be the summation 1 to n of 1 plus I over n squared times 1 over n. All right, the first thing I want to do is try and get this to be just like one fraction if I can. So what can I do here? I've got 1 plus I over n. Well, I'm going to be taking this and squaring it. It might be easier for me to just say this over that, one single fraction squared. If I've got 1 plus I over n, I can't add these as is because they've got different denominators. I can think of this as 1 over 1, but this has an n in the denominator. So if I multiply 1 by n over n, that'll give me the same denominator as I over n. So this would end up being n over n plus I over n, or putting this together, n plus I over n, and then that squared. Let's write that down. This is the same as the summation from I equals 1 to n of n plus I over n, this squared, and then I'm multiplying by 1 over n over here. Okay, n plus I squared. Off to the side. You can do this in your head, but you want to be sure, do a little box, n plus I, n plus I. I'm squaring this, so I'm multiplying that to itself. This is n squared plus ni plus another ni here plus I squared. So this is n squared plus 2ni plus I squared. And then n squared on the bottom, that'll just be, well, n squared. So this is equal to the summation I equals 1 to n of the top part is this, n squared plus 2ni plus I squared over n squared. And I'm multiplying that to 1 over n. Now what I'm going to do is I'm dividing this by an n squared and then multiplying this by 1 over n. So what I can do is break this up and say that this is really n squared plus 2ni plus I squared. That quantity times 1 over n squared, and then just multiply that 1 over n squared to this 1 over n to give me the summation I equals 1 to n of n squared plus 2ni plus I squared, this times 1 over n to the third power. Now, why would I want to do that? Remember that n is just some number. Therefore, 1 over n squared, and 1 over, in this case, n to the third is going to be just some number, some constant. So I can take this and pull this out to the front and say this is equal to 1 over n to the third. Now do the summation part. I equals 1 to n of n squared plus 2ni plus I squared, which will then allow me to break up each of these into their own separate summations. So I've got 1 over n to the third all the way on the outside, big brackets now, and let's give each of these their own summation. The summation I equals 1 to n of n squared plus 2n, again, just like 1 over n to the third was a number, 2n is just a number. So I'm going to bring that to the front of this summation. I equals 1 to n of I plus the summation I equals 1 to n of I squared. This looks like things got more complicated, but there's a reason I wanted to break this up the way that I have. Now I can bring over my summation formulas, and I can say this first summation is of n squared. N squared is just a number. Just like summation 1 formula here says if I'm taking the summation of just a number, then I can do whatever n is times that constant. In this case, n is n. My constant is n squared. When I multiply them together, I'll get n cubed. Okay, so let's start there. I've got 1 over n cubed here, big brackets. This first part will be n to the third power. Okay, and I'm actually going to write this a little bit higher, and you'll see why later. Plus 2n, okay, times the summation of I. Okay, the summation of I is n times n plus 1 over 2. So this will be n times n plus 1 over 2. Okay, I guess I don't have to bring this up just yet. Maybe it'll be cleaner if I do this in 2 steps. All right, then plus the summation of I squared. I squared is n times n plus 1 times 2n plus 1 all over 6. Okay, so that's going to be n times n plus 1 times 2n plus 1 all over 6. All right, let's try to clean this up a little bit. This 2 will divide out with this 2. And then this n times n plus 1, let's distribute that through. That'll be n squared plus n squared plus n. But then I've got another n over here. So n squared plus n, but then multiplying that, distributing that to each of these, that's going to give me n to the third plus n squared. Okay. So let's start writing this out. This is equal to 1 over n to the third, big bracket. Now I'm going to put this up in the air a little bit, plus this divided out, but I'm still going to have it up on top. I've got n squared plus n. I'm distributing another n, so this is n to the third plus n squared plus, now distribute this. This is n squared plus n. And I'm multiplying this n squared plus n to this 2n plus 1. So what I need to do is another box over here. I'll have n squared plus n times this 2n plus 1. So 2n to the third power. Here I've got plus n squared plus 2n squared over here, and then plus an n. So all together, 2n to the third power plus 3 of these n squareds plus an n. 2n to the third power plus 3n squared plus n over 6. Now the reason I left these up here, because I'm going to turn these into fractions, because this is a fraction with denominator 6. Currently, these have a denominator of 1. If I want to get this to be a 6, then I'm going to multiply this one by 6 over 6, making it 6n to the third power over 6. If I multiply this top by 6, by this bottom by 6, then distributing that 6 through, I would have 6n to the third plus 6n to the second all over 6. All right, so now this is 1 over n to the third, big bracket, I can add all of these together and have one big fraction with a denominator of 6. So what goes on top? Combine like terms. I've got 6n to the third here, another 6n to the third here, and 2n to the third here. 6 plus 6 is 12, plus 2 gives me 14n to the third, plus, how many n squareds? I've got 6n squared here, plus 3n squared here. That's 9n squared total, plus, how many n's do I have? A single one here, n. Now this 1 over n to the third is being multiplied to this big fraction, which means that I can just bring this n to the third to the bottom and make it 6n to the third. So now I've got 14n to the third plus 9n squared plus n all over 6n to the third. And that is just the summation. Now I have to find the limit of this as n approaches infinity. Now, in the last section, we learned that if I'm doing the limit as n approaches infinity of some rational function, then I can look at the highest powers, the leading powers in the numerator and the denominator. If the highest power on top is greater than the highest power on the bottom, then the limit does not exist. If the highest power on top is less than the bottom, then the limit is 0. However, in this case, they're equal to each other. The leading power on top is 3n to the third. The leading power on the bottom is 3n to the third. If that's the case, then I look to the ratio of the coefficients. I've got 14 here over 6. So that means the limit as n approaches infinity of s of n is equal to 14 over 6, which I can reduce to 7 over 3. That's the answer I'm looking for. So when can this be useful? Here's an example, the area problem. This problem involves finding the area of the region bounded by the graph of a non-negative continuous function. So it's nice and smooth. The x-axis and the vertical lines x equals a and x equals b. So let's say I've got this curve here, and I want to know what is the area from this to this under the curve and between that and the x-axis. If this were a nice shape, a geometric shape, say a rectangle, I could find that. Just do the length times the width, base times height, whatever you want to do. If it is a triangle at 1/2 base times height. If it was a circle, 2 pi r squared. However, that's not the case here. This is some weird shape, and I can't find it by simply using one formula. I also can't find it by even breaking this up into nicer shapes, like you've done in geometry. So what can I do? What we're going to do is we're going to approximate this using rectangles. Here's the area of a plane region. Let f be continuous and non-negative, so the function, on the interval a to b. The area A of the region bounded by the graph of f, the x-axis and the vertical lines x equals a and x equals b is given by the following. I'm going to be using multiple rectangles. Now rectangles have a height and a width here. To find the height, I'm going to do the function of a plus the quantity b minus a times I over n here, times the width, that's going to be b minus a over n. Now, what does this actually mean here? And this is as n approaches infinity. Now, what does this mean? If I look at this problem, it says use 5 rectangles of equal width to approximate the area of the region bounded by the graph of f of x equals 6 minus x squared. That's your function. The x-axis and the lines x equals 0 and x equals 2. All right, so I've got this curve, and I want to find 5 rectangles that fit inside there. Now each rectangle, because the entire area, because I'm going from 0 to 2, I'm going to do 2 divided by 5 to get the width of each of these. That's 2 fifths. Then for the height of these rectangles, I'll be using this curve, and the height of this rectangle, one corner is going to hit this curve right here. This is at 2 fifths. At 2 fifths, the height of this rectangle is f of 2 fifths. So I plug in 2 fifths to my x, and I find the height here. The next one would be at 4 fifths, or 2 times f of 2 fifths. At 4 fifths, I would have this height, and then times the width, 2 fifths. Then the third, then the fourth, then the fifth. Now, I could find it that way, but it will take a little bit of work, and that's just for 5 rectangles. Imagine if I asked you to do 10 rectangles or 20 rectangles or 100 rectangles. You wouldn't want to sit here and find the areas of 100 rectangles and then add them together. Instead, use a summation. Here we'll use the sum of the areas of the 5 rectangles by using the summation 1 to 5 of f of 2I over 5 times 2 fifths, or in other words, the height here times the width. Plugging in 2I over 5 into my function 6 minus x squared, that's going to be 6 minus 2I over 5 squared. So that's where this comes from. And then my width for each of these rectangles is 2 fifths. Now I'm going to scroll down, and then we'll come back to this image later. Let's find this summation. All right, firstly, I see that I've got 2I over 5 squared. This means I'm going to square the top here and square the bottom here. This is going to be equal to the summation I equals 1 to 5 bracket of 6 minus 4I squared over 25. That times 2 fifths. All right, this 2 fifths is just multiplying to this, so I'm just going to bring it out to the front. So this will be 2 fifths times the summation, I equals 1 to 5 of 6. And then I can actually break this up, minus, let's do a bracket around this whole thing, minus the summation, I equals 1 to 5 of 4I squared over 25. Now, 4I squared over 25, this is the same as saying 4 over 25 times I squared. So I can take this 4 over 25 and bring it to the front of this summation here. Let's do that. 2 over 5, big bracket, times the summation of I equals 1 to 5 of 6 minus, bring this 4 over 25 to the front of this summation. The summation of I equals 1 to 5 of I squared. Okay, so now let's look at our summation formulas. 6 is just a constant. So formula 1 says do the constant times n. This will end up being 6 times 5 here. Let's write that out. This is 2/5 times 6 times 5 for the first part, minus 4 over 25, and then I squared. So the summation for I squared is n times n plus 1 times 2n plus 1 all over 6. So n is 5, remember. So every time you see an n, replace that with 5. That'll be 5 times 5 plus 1 times 2 times 5 plus 1 all over 6. All right, now if you wanted to and you were really careful, you could put all of this into a calculator, but it's a lot. So I'm going to piece this together. This is 5 times 5 plus 1 is 6 times 2 times 5 plus 1 would be 11. So 5 times 6 times 11. Then I'm going to divide that by 6 here. Now this whole piece is 55. I'm going to multiply it to 4 over 25. So multiply by 4 over 25, which gives me 8.8 for this part. 6 times 5 is going to be 30. 6 times 5 is 30. Now we subtract the 8.8. So this is 2/5 times. This was 30 minus 8.8. But then I discovered that 30 minus 8.8 is 21.2. So this is 21.2 times 2/5. So the area is roughly 8.48 square units. .48 square units. Now I'm going to scroll back up and let's look at that image again. This area is about 8.48 square units, but it's not, the area that we found is an approximation. It's not perfect. Okay, why do you think that is? It's because of these empty spaces here. I've colored them in pink. When I make 5 rectangles, the space that those 5 rectangles take up, the area of those 5 rectangles, misses the little bit of pink here, the little bit of pink here, 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 and here. So what would be a better approximation then? Well, if instead of 5 rectangles, I used 10 rectangles, then that empty space would minimize a little bit. If I used 20 rectangles, it would get even better. 100 rectangles, that would be really good. But the best would be if I used an infinite number of rectangles. Because if I used an infinite number of rectangles, then that means that this space would be, well, non-existent. Let's try that. Find the area of the region bounded by the graph of f of x equals x squared and the x-axis between x equals 0 and x equals 1. Now, it doesn't say using a number of rectangles, so we're assuming that we're going to be using an infinite number of rectangles, or we're letting the limit of n approach infinity. So I'm going to use the same formula. The area is about the summation of I equals 1 to n of the function evaluated at a plus b minus a times I over n, and then times b minus a over n. This is your height, and this is your width. First, let's fill in. What is a? What is b? Well, a is 0, and b is 1. So I'm going from 0 to 1. So a is 0, b is 1. Then the width, that's this part, b minus a over n, that would be 1 minus 0 over n, or just 1 over n. The height, this is f of a is 0 plus b minus a would be 1 minus 0 times I over n. The function evaluated at this. Now this will end up being f of 0 plus 1i over n. So just 1i over n, or I over n. The function evaluated at I over n. So I go back to my function here. My function is x squared. So I plug in I over n into x for x squared, and that'll give me I squared over n squared. This is the height. And then once I have my height and my width, we're going to approximate the area as the sum of the area of n rectangles. All right, so this will be the summation of I equals 1 to n, and I found this part, my height, to be I squared over n squared times b minus a over n, that's my width, that was 1 over n. Okay, this is the same as saying the summation of I equals 1 to n of I squared times 1 over n to the third power. I'm just going to bring this n squared over to this. That's because 1 over n to the third power, this is just a number. Okay, now we might be letting n approach infinity, but we treat this as a number, and so as this is a constant, I can just bring this to the front of my summation. So this will be the summation. Oh, let's do this, bring to the front first. This will be 1 over n to the third times the summation of I equals 1 to n of I squared. Which means we need the summation formula for I squared. That's n times n plus 1 times 2n plus 1 all over 6. So I'm going to replace the summation of I squared with this here. All right, so this is 1 over n to the third. This summation ends up being n times n plus 1 times 2n plus 1 all over 6. Okay, let's distribute this n to this first one. That'll be n squared plus n. Now I'm multiplying n squared plus n to this 2n plus 1. So let's do a box over here. I've got n squared plus n, and then 2n plus 1. When I multiply this, I'll get 2n to the third power plus an n squared here, plus 2n squared here, and then plus an n. So this is 2n to the third power plus 3n squared plus n. So the top part is 2n to the third power plus 3n squared plus n over 6. Now I'm multiplying this by 1 over n to the third. So that means I can just make this 6n to the third. Now this is the summation. Now let's find the limit of this as n approaches infinity. So the area is going to be equal to the limit as n approaches infinity of 2n to the third plus 3n squared plus n over 6n to the third. And just like the last section again, as I'm taking the limit as n approaches infinity, I look at the leading powers. What's the highest power in the top? What's the highest power in the bottom? If the highest power is on top, okay, say this is n to the fifth, and then the bottom is n squared, then the limit does not exist. If the highest power is in the bottom, let's reverse that. The highest power is 2 and the bottom is the highest power in the top, and the highest power is 5 in the bottom, then the limit would be 0. But when they're equal to each other, I've got n to the third here, n to the third here, I look at the leading coefficients. This is a 2, this is a 6. This means that this is going to be 2 over 6, which reduces to 1/3. The area under the curve is 1/3. This is another really helpful tool that's going to be used quite often in calculus. Summations and limits are very powerful. Make sure you study these, and if you have questions, let me know.